Welcome to your lesson on evaluating functions. Let's begin with why we even have something called function notation. Why is it important? Take a look at these two equations. You have y equals 2x plus 5 and y equals negative 3x plus 15. Let's say somebody told you x value is 3. What would you say y is equal to? Well, you could put 3 in here and get an answer of 11, or you could put a 3 in there and get an answer of 6. So you're left wondering, are they asking me for this one or this one? I don't know. Is it 11? Is it 6? What's happening? This gets us to why we have functions notation in the first place. Because to deal with this problem, we have what's called functional or function notation. Basically, since these two functions look identical, you can't differentiate between one and the other. Using function notation, each function can have a unique name. For example, this first one can be named f of x. So instead of y, we put f of x. So we mean there's this function here, and the input value is x. And then the other one, here, we named it g of x. You're unlimited in what you call a function. It can be any letter. This doesn't have to be x either. You'll see more examples of that later. But basically, now we've named each function individually, so you can see which one's which. So now, instead of saying x equals 3, we can say f of 3. That means into this function, we put an input of 3. So that x is replaced with a 3. Again, that means into this function, put an input of 3. So if you see that, you know your answer must be 11, because it tells you clearly that that x value of 3 is going into this function. And if you're looking at this function, it could give you g of 3. That means clearly we are now substituting an x value or an input of 3 into this function. So there's no confusion like there was up here. Now it's very clear which function we're using. Alright, let's take some notes. So grab the notes page that was provided to you. And let's begin here. As you watch, please add notes to your notes page. An equation that is a function may be expressed using functional notation. The notation looks like this. We just saw some examples of that. For example, this is f of x, and we read that as f of x. Here we have this, g of x, read it as g of x. Here's a different kind of function. Again, we can use any letters we want. Here we have c of t, and your options are unlimited. Above, the x or the t, so these x's and this t here, are the input values. So the thing you see here are the inputs, and the f of x, g of x, and c of t are all the outputs. So this is the output, this is the output, this is the output, because each of these is like the equivalent of y in the equation. Okay, let's look at an example here. Here we have an equation. It can be written in functional notation. As we said, we don't have to use y, we can use functional notation, f of x. And now let's say the input is 4. This means that x equals 4. So again, in functional notation, let's begin with xy notation. Xy notation, you would have it like this, right? If x equals 4, then you replace that x with 4. So there's a substitution. Make sure to use parentheses, and we know the answer is y equals 12. Using functional notation, we can write f of x equals 2x plus 6. So the same equation, but we're using function notation here. And now when we say x is 4 again, this part here becomes the input value of 4. And this part looks the same as on this side. So we substitute a value of 4 for the x, and we get the same answer. But now when we write the answer, we don't just write y equals 12, we write f of 4 equals 12. So again, this is better notation than this, because here, if you didn't see these first two steps, you'd look at that and you'd say, okay, y is 12, but I don't know what x value was put in to make 12. Over here, it's clear what was put in, so the x value of 4 was put in, and the output was 12 as a result. So in this one statement, we can see the input and the output, which makes it more clear. Okay, let's look at another one. Let's say you have an output of 16. So the output is like the y value, right? So this means y is 16. So in xy notation, if we use that same equation, now if the output is 16, we're replacing y with 16. So 16 goes here. And now we're going to solve for x. So subtract 6, and then divide by 2, and we have x equals 5. Let's try the same thing in functional notation. There's the same equation written in functional notation. Again, the output is 16. So the output, the f of x, is replaced by 16. A common mistake here is students will write 16 here and they'll keep that x there, but this whole thing is like your y value, so this whole thing is replaced by 16. So 16 equals 2x plus 6. And again, you solve that the same way as here. Minus 6 divided by 2, and you get the same answer. Okay, so try this one. Here's XY notation for this one. What would that one look like in functional notation? There it is. Okay, now x equals 2. So find out what y would be. Alright, substitute a value of 2 and you get y equals negative 4. Do the same thing in function notation. Alright, that means we have f of 2, the input is 2. We do the same solving here, f of 2 equals negative 4. Now, let's say y equals 8, so solve for x. So you replace y with 8, solve this one backwards here, and you get x equals 6. Try in functional notation. This time, if y equals 8, that means f of x is 8, so we replace this thing with 8 right here, and then it becomes the same solving we did here. Alright, so that's xy notation versus function notation. Let's look at this one. Now that you have an understanding of how it works, this one's not on your page, but let's take a look and see if you can answer these questions. First of all, let's look at g of 2. So it says given the graph of g of x. This graph here is of some function g of x. So we've graphed this function. And we say g of 2. So think about that. What does that represent? Is that the input or the output? So what do you think the answer to that should be? Well, I hope you came up with 2, and the reason for that is this. This 2 here is an input. Remember that one that goes in there is the input. So when you look at this function, the input values are the x values. So you're like, when x is 2, that's our input, you go up to the function. When x is 2, oh, y is also 2. So when x is 2, y is equal to 2. That's how that works. So try another one. How about this one? Okay, I hope for this one you got 0.5. In this one you look at the input again. This is the input. The input of negative 1 goes into the function. So you look at the x values, which are the inputs. You go to negative 1 right here. You go up to the function, and you're like, oh, right there. What's the y value there? It's about 0.5. And finally, let's flip this around. It says g of x equals negative 1. So if g of x is negative 1, it's telling you what the y value is. And then it says find x. So for that one, I hope you got negative 3. Because we have a y value of negative 1, so you go here on the y to negative 1, you go across, and you see, what is the x value right there? The x value is negative 3. Okay, on your page you have this one. Find each of these, so try to find f of 2. Okay, f of 2 is 16, you can check the work there. F of a plus 1, this is a little different. That means, again, the input now, here the input was 2, so 2 replaced the x there. This one, don't look at it as something more confusing, it's the same idea. Now the input is a plus 1, so this x is replaced by a plus 1. So you do it like this. That x value became what your input is. So there it is. And now you can simplify this by multiplying this parenthesis here. 4a plus 4 plus 8, you can combine the 4 and the 8, and you get this. Alright, so try this one, same idea. This is your input into this function. Okay, here again the input is negative 4a, so that x is replaced by the input of negative 4a, and 4 times negative 4 is negative 16a, and then we have the 8 there still. Alright, and this one is one of those ones where it gives you the f of x equal to this, means it gives you the y value, and says what is x. To solve this one, you replace the f of x side, the y side, with negative 10, and you solve backwards. When you solve that, you should get x value of negative 9 halves. That was 18 over 4, which can reduce to 9 halves, which is negative 4.5 if you did a decimal. Okay, here's another one. Find each of these. For this one, we put negative 3 into this function. The input is negative 3, goes in here, negative 3 here, and again we're going to keep writing this like this. That becomes positive 12 minus 20, negative 8. Alright, now your input is all of this. So this x value is replaced by all of this. Here we go. So that x has been replaced there, and negative 4 times this is negative 20x squared. So we'll see that answer in a moment, and this one, try it as well. Okay, so this one works out to Sorry, these came up at different times. This one works out to this, and this one here works out to a equals 9, because now you're looking for the a value. It tells you the y value is 16, so that is replaced by 16, and you solve backwards to get a. Okay, great. Here's a few more for you to try. Let's see how you do. Check your work for those, A, B, and C. And check your work for D and E as well. This last one here, E, when you put the input of x plus 1 in here, notice that x plus 1 replaces that x there, so you have x plus 1 in parentheses squared, and that can be expanded. We can remember from our quadratics unit into this, and simplified until you get to this form. Okay, I hope that makes the evaluation of functions more clear, and please follow this up with a second video on using functions as models for real-life situations.